In this video, I answer student questions about solving the more complicated circular functions and then move on to the curriculum content, which is to look at the applications of quadratics. Enjoy! Okay, so let's get a start. We've hit 5:30. Cool. So before we get into the actual agenda for today, we're just going to have a look at solving some of the harder circular function stuff. Very briefly, we'll look at how you solve circular functions to begin with. So in all circumstances, you're trying to get your circular function into a spot where you have an exact value expression. That means you have a circular function on one side and one of the exact values on the unit circle on the other side. From there, you may or may not need to simplify things with substitutions, but from there, you're effectively just trying to find where your circular function exists on the unit circle. That's the gist of it. So if we look at a nice and simple example, welcome here. If we look at a nice and simple example, we have just cosine equals √2/2, and we're solving that between 0 and 2 pi. No rearranging is particularly necessary here. You've got a cosine on one side and you've got an exact value on the other. All we're doing from there is trying to figure out where does that appear on the unit circle. So you look for all the spots on the unit circle where x is equal to √212, because cosine is for your x, and it's going to give you the solutions pi/4 and 7 pi/4. And that becomes your final answer for the question. Sometimes you might need to do a bit of rearranging before you get there. So you're going to have, in this case, rearranging to get the √3/2 on its own. Exact value on one side, circular function on the other. Exact same idea. If you have different domains, you're just going to go backwards and forwards on the unit circle. So if we're looking for where sine is equal to 0, but it's between -pi to pi, you still find all the spots, but you have to give it in the equivalent negative and positive angle instead of just purely positive. If it gets more complicated like this, my recommendation is to take whatever's inside the brackets of your circular function and replace it with a substitution. So what that effectively does is take some of the guesswork out of how many solutions you need to find. Because whenever you have dilation factors, and depending on how big your translation is, that might also impact it. But whenever you have these factors in there, it's likely that the initial assumption of two solutions between 0 to 2 pi is going to be false. These dilation factors and translation factors will effectively change the effective domain. So to reveal that properly, one of the things I like to do is take whatever's in the brackets as a substitution. In this case, u equals all of that. And from there, we have to change up this x domain to make it in terms of u. So from there, you just take your x value, shove it into the equivalent spot on the u equation. Do that for the lower bound, do that for the upper bound. And what you're left with at the end is a nice and simpler equation to solve. And it's simply just where is cos equal to 1/2 between pi/2 and 9 pi/2. That is significantly easier to solve. X equals 1/2 there. These are your two coordinates, and you're simply just going to add 2 pi repeatedly until you get through the full domain, which is from pi/2 to 9 pi/2. So if you repeatedly do that over and over again, you're going to get this big list of u values. From there, you're going to consult your domain. So ours is from pi/2 to 9 pi/2. So you want to make sure that everything in this list is between that domain. Pi/3 is too small. 17 pi/3 is too big. The way you can figure that out, simply just convert your divide by 2 and divide by 3 into the same denominator, and then compare them from there if it's ever too difficult to see the difference. But if you do that, you'll find that the upper and lower of that list should be removed, giving you these 4 solutions in terms of u. But we don't want them purely in terms of u. We're trying to solve for x. So it's at this stage where you then put in what the x equivalent actually was, and then rearrange this for x. So that's going to mean dividing everything by 2, and then subtracting pi/4 from everything. The net result of that is all of your x values are between 0 and 2 pi, and there's no longer any guesswork. Do I have to go one forward and one backwards? No. you've already found everything in there because you've done that work ahead of time to rewrite your domain, your effective domain. Any questions at all, please put them in the chat or just hop off mute. More than happy to go and explain anymore. Where they get a bit more complicated is when you have multiple circular functions in the same equation. So one of the ways you can handle this is with a null factor law approach and factorization. So when both of the circular functions in your equation are the same, you can take those out as a common factor. Cos squared and cos, common factor there is going to be cos. From there, you have two things that are multiplied together to give 0. That is a null factor law. And so under those circumstances, you now have cos equals 0 or cos plus 1 equals 0. So you just solve each of those individually. Solving cos equals 0 is going to be these spots. Cos plus 1 equals 0, you just rearrange, and then it's going to be this spot here. So the final answer is going to be you join all those answers together. So you've got the pi over 2 and 3 pi over 2 from here, and the pi from here. That's one way to go about it, solving by a null factor law. If the circular functions are different, specifically if they are sine and cos, it's pretty likely that you can solve it by using tan. Now there are some situations where it won't be necessarily possible there, but in this case it is because it's sine and cos without any powers associated there. So for me, I've started to rearrange it a little bit. You don't have to start by rearranging. The main key takeaway for this one is that you want to divide both equations by cos. When you divide both equations by cos, one of the coses will cancel out down to whatever it ends up being, in this case, -1. And the sine divided by cos will simplify down to tan. The effect here is that we now have only one circular function in the equation, which we can now solve using the methods we're already used to. Where is tan equal to -1 over root 3? Well, it's going to be these spots, rearrange, rearrange. Nothing different from what we've just discussed from this point onwards. So main takeaway being, if you have both sine and cos in your equation, pretty likely that you'll be able to solve it using a tan equation equivalent. Now, that's all I have in my notes for these. I do have another one that was unique, which was in my second tech-free practice sack, which was, well, ignore that it says general solution for now, but it's what happens when you have a sine squared and a cos that makes things just a little bit different. Fundamentally, we're still trying to get this down to a null factor law situation, whether we use factorization. We're still trying to get it down to an exact value expression, whether you can get there using null factor law, factorization, converting to tan, whatever you've got to do to get there is all that really matters in the beginning. Now, the method that we haven't looked at here is using the trig identity, sine squared plus cos squared is equal to 1. The reason why we do that is because that gives us a way to convert our equation to only having cos in it. So if I were to go to the handwritten bit now, just by typing out or writing out the identity, sine squared x plus cos squared x is equal to 1, you'll notice that you can rearrange this to make either sine or cos as the subject of your equation. Now, in this case, we want cos to be in our equation, so we're going to rearrange this one for sine so that we can replace it. So you're going to have sine squared x is equal to 1 minus cos squared x. And so when you have your equation, which was 2 sine squared x minus 1 equals cos x, you can now replace this with this. That gets you to a situation where you only have cos in it. So what that does is 2 bracket 1 minus cos squared x. You're still going to have that minus 1 equals cos x. Now, okay. From here, we can do a bit more rearranging. We're trying to eventually get to a situation where we only have one circular function in here. We've made it a bit simpler in that we both have only two causes in our equation, but we still need to get to a place where we only have circular function equals exact value. So let's do a bit of expanding just to make that easier. So 2 goes into there, minus 2 cos squared x, still going to have that minus 1 cos x, 2 and the 1 will cancel down to just 1. Minus 2 cos squared x plus 1 equals cos x. At this stage, does anyone have any ideas how we might simplify it further from here? It's a technique we use in actually another area of study as well, namely exponentials. I'll let you chew on that for a little bit. Okay. One thing I'd point out will be the powers here. You've got a cos squared, you've got a cos, and you've got a no power involved. I'll write something pretty similar, just to the right of it. What do you do when you have e to the 2x plus e to the x plus 1 equals 0? Very similar thing. You've got these descending powers. That's a hint. I can't tell if you're thumbs up because you want to speak or if you're just saying yes.
Quadratic. Yeah.
Yeah, exactly, quadratics. So the method you'd use for exponentials here is you'd say, I don't know, let a equal e to the x. This will be a squared plus a plus 1 equals 0, which may or may not have a solution. I did just make that one up on the spot. How might we apply that to this? What substitution might we do?
Sub in like a letter for cos.
Yeah, precisely. Minus 2, let's call it capital A squared, plus 1 equals capital A. This is just a quadratic now. So get everything to the same side. So 2a squared over there, 2a squared plus a minus 1 equals 0. You could do quadratic formula. You could do the cross product method for factorizing. Point being, you're now just solving a quadratic from here. Who knows how to factorize that or solve it in any other way?
Could we multiply the A and the C term and then do like grouping to like factorize it?
Sure. What would that look like?
Um, so you would want to see like 2 and -1 is equal to -2.
Yep.
And then you'd want to see what two numbers add up to that multiply to -2 and add up to +1, which is negative. So that's a -1 and a +2. So what you want to do is you do 2a squared minus 2a.
Okay. 2a squared
Sorry,
minus
2a,
2a.
yeah, 2a squared minus, no, sorry, plus 2a.
Okay.
Minus a minus 1.
Okay.
And then what you do is just through grouping, you take out 2a from the first two terms, and then put in a and 1. And from the next one, -1, then a plus 1.
Yeah.
And then because there's like two common brackets, you have 2a minus 1 times a plus 1.
Yeah. Yeah, so you got your, well, hang on. So you're taking a plus 1 out the front again, right? And that's 2a minus 1, like that, yeah?
Yeah.
Sweet. Yeah, and because that all equals 0, what you've now got is a null factor law. A plus 1 equals 0, or 2a minus 1 equals 0. From there, you've got a equals -1, or you've got a equals a half. Just keeping in mind that a was cosine. So now it's just, where is cos equal to -1, or cos equal to cos equal to +1/2. Now, that's a unit circle thing. I'll bring up the unit circle just for fun on the screen share. That way anyone who hasn't seen it or memorized it yet can use that. I'll even put that in as a screenshot actually. Okay. Screenshot incoming, and we wanted to do it. Oh, it did say general solution for this one, but we'll pretend it was just solve from 0 to 2 pi. What would the solutions therefore be?
For -1, would it be pi?
Yep, pi, perfect.
And then for a half, it would be
pi/3.
Pi/3 is one of them, yep. One more in there. Whenever it's the interquadrant angles, there's always 2.
5π/3.
5π/3, yeah, there it is. Sweet. So those were the two for cosine being a half. If you divert your attention to the screen share, I can highlight those. The cosine solutions will always be vertical from each other, so that's the nice little hack around that. Just wherever you find your first one, just look vertically down or up, whatever that looks like. And then the other is right over here, where cos is equal to -1. Cool. So that would be, if you're just solving from 0 to 2 pi, you would give those as your answer. Now, what we haven't really touched on just yet, at least in this class, is how that works for a general solution. General solution, literally all you're doing is adding 2 pi n to these solutions. That's pretty much it. So when you give your final answer, you say x equals pi plus 2 pi n. And you're going to have, now there's two ways you could do this one. You could then again add 2 pi n to both of these, in which case you got pi/3 plus 2 pi n and 5π/3 plus 2 pi n. When you're doing this, just make sure to put n is an element of z for the integers. That's like a very refined way or very specific way of giving the solution there. When it comes to cos, however, I kind of, when I said 0 to 2 pi initially, that was more so just because I made my own little restriction there. When you're doing general solutions, no such restriction is implied. So instead of giving 5π/3, what you could have done is plus minus pi/3 for this bit here. So what that ends up meaning is you ignore this solution here, you put a plus minus there, and there's just one less line of working for you to give. So that's that. So we've looked at a few different ways to solve more complicated things. There's null factor law, so factorization. There's this, which might require you to use the trig identity, or there was converting to tan, which I've got 2 more examples, or we could do both of those. Do you guys want to do more examples of this, or move on to the applications of quadratics? That sounds more enticing.
Probably move on.
Move on? Sure. So for those who do want to practice it, this is just in the SAC 1, which is question 7, and this is in the SAC 3, which is question 2. And those will all be in the school module for practice X. All right, let's kill some of those. Cool. So first up, simultaneous linear and quadratic. One of the applications here is usually around like if your linear is tangent, if it cuts at 2 spots, or if it cuts at 1 spot. If it has one solution, we consider that to be touching at a single, one solution means touching at a single spot, the linear is considered tangent. If it's 2 solutions, that's what that looks like. If there's no solutions, they won't touch at all there. And so when we're solving simultaneous linear and quadratic, if there's no like additional unknowns in here, then effectively all that's happening is you solve it like any other simultaneous equation. You equate the two things together and you solve for x. So equation 1 here, equation 2 here, solve for x, you only get one solution in this case. So whether it's one solution, no solutions, or infinite solutions, if there's no additional unknowns in there, you don't actually change how you handle the question. And so literally all that ends up being is you do the exact same thing every time. You get your x value by equating the two things together. You sub that x value back into either equation to get the equivalent y at that spot. So here's an example of where it would be two solutions. Again, equation 1 equals equation 2. Simplify, simplify, simplify. In this case, solved using factorization. You get two x values, you get two y values from there. If there's no solutions, then you'll find that this quadratic will not be solvable. Because if you do discriminant of this thing, you'll find it's negative. Whenever you have negative discriminant, there is no solutions there. So we come now to figuring out how do we handle ahead of time how many solutions a quadratic is going to have. Again, that is going to be discriminant, but more specifically, the discriminant that you look at will be on the resulting quadratic after equating the two linear together, not on this quadratic up here. So you have some two generics, whatever. You equate the two together, you get them to the same side, you combine the like terms. This is all stuff we've seen, even if it looks a bit nasty because of the numbers involved, or the letters involved rather. You do discriminant of this thing here. Now, one pro tip around here is if this quadratic can be simplified further by like dividing by 2 or whatever, don't do that. That will break it. So if I give an example in the handwritten notes, let's say you've got a linear and a quadratic, you rearrange them together and you got something like 4x squared minus 4x plus 4 is equal to 0. All right, let's pretend we had that. You want to find discriminant of this. You don't want to find discriminant of this. Because even though you could divide everything by 4, it just breaks things. Right. This quadratic is very different to the graph of this quadratic. So when you're looking for a number of solutions, you end up getting different results, things break. The next few examples just show you what's likely to happen if you have no additional unknowns in there. But where this becomes more interesting is when you're solving these so-called literal equations, which simply means you have an additional unknown in there. So back to the screen share, we now have a quadratic and a linear with an unknown k involved in there. And we want to figure out k value such that we only have one solution for this equation. So again, everything starts out the same. You start by equating the two equations together, collect the like terms. This is the quadratic that you're now going to do discriminant of. So discriminant is b squared minus 4ac. There's your b, there's your a, it's the coefficient of 1, and this whole thing is your c. Plug them all in. This ends up being just a linear to solve. Square through, simplify, 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 and you'll find that if k was negative 13, these would be tangent to each other. They'd only touch at a single point. For two solutions, you want your discriminant to be greater than 0. So you're doing the exact same scenario, but now you're putting a greater than 0 instead of an equals 0. Simplify, simplify, simplify. K is now greater than negative 13. For no solutions, discriminant wants to be less than 0, and so it's going to be the opposite. You're going to be less than negative 13. That's the gist of those there. Does anyone want to practice any of those before moving on to the applications where you've got like families of quadratics like this, or you've got like maximums of like area and that sort of stuff? Anyone want to practice these beforehand?
Should be fine.
Should be fine. Easy. Okay. Next up. So, families of quadratics. So this is the kind of thing where you have pretty much a fully unknown quadratic to start with, and your goal is to figure out all the unknown terms in there. What are their values? You'll need to be familiar with the three main forms of quadratics for this. So you'll need to know the polynomial form, or the expanded quadratic form, general form, I guess, of quadratic. You'd need to know the factorized form for axes-intercepts, and you would need to know the turning point form if the information that you're given is a turning point. So, very easy. If the information you're given is a turning point, start with a turning point form of your quadratic. The reason why I'm mentioning this is because it may not be given to you what quadratic you should start with. It's likely you'll have to choose your own form. So, turning point was one of the key features we were given. That immediately gives us what our B and C values should be. This is shifted 1 to the right and 3 up. This should mean x minus 1 and plus 3 at the front. So, all we're doing from here is solving for A. Doesn't matter what form of the quadratic you use, you'll always have this A out the front of it. The way we solve for A is always by subbing in the additional known point, whatever that happens to be. So in this case, it's 0, 4, y value of 4, x value of 0, simplify, 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 A equals 1. So when you put it all together, you just replace A with 1, or in this case nothing because we don't actually represent ones, and that gives you the final equation for the curve. If you have x-axis intercepts, then the best form for this would be the x-axis intercept form, right? Because if you have a cut at -2 and +1, the factors must therefore have been x plus 2 and x minus 1. Fairly straightforward there. You don't necessarily have to use axis intercept form. Because you have 3 points here, you could do a simultaneous equation with ax squared plus bx plus c. I would just strongly advise against it because it takes a long time. Whereas with this one, you've just got the points and that's it. Again, we're solving for A. Lo and behold, we have another known point to work with, and so we plug that into where we left off. In this case, we get A equals 3. It's fine for you to leave the equations like this, unless otherwise specified. You can leave it in there factorized, completed square, or otherwise. This is what happens if you can't use any of the forms, so that's not quite a turning point, and you've got 2 other points in there. This is where you're doing a 3-way simultaneous. Usually they be nice to you, and they give you the y-intercept as one of your values. The reason why that's nice is because when you have your ax squared plus bx plus c, subbing in that x equals 0 very quickly just gives you the c as the y value at that spot. So in this case, c equals 5. But from there, you just sub in the other remaining points into your ax squared plus bx plus c. That gives you your 2 equations, and you solve those simultaneously, however you like to solve simultaneous equations. I've done elimination method, so adding these 2 equations together, that will cancel out this b term. Alternatively, could have done subtraction, cancelling out the a, could have done substitution, anything's on the table. That's going to give me a equals 2, b equals -3, and all I do is put in my a, b, and c into the quadratic. Do I need to go into any more detail on that? Okay. And yeah, any other time, just put up a question in the chat or hop off mute. Finally, we look at maximum/minimum problems. So this is where you're trying to find either the maximum or the minimum of a certain quantity. Now this goes beyond just solving quadratics. This is also applicable to polynomials of other kinds, and it even goes to circular functions. Sometimes you do end up doing maximums of circular functions. Rarely exponentials or logarithms. And I have seen some strange ones, literally just an hour ago actually, where they've done hyperbolas and other stuff as well that have like restricted domains. You still use the exact same procedure here, because a lot of the time your maximum or minimum is going to be a turning point. And so you can use, in this case we won't look at calculus necessarily, but you could use calculus by finding derivative, set it equal to 0, and that'll give you your turning point. But okay, so step 1 is just get an equation which describes that quantity that you're looking for, whether it be area, whether it be volume, could be whatever. but specifically you want it only in terms of one variable. From there, you want to sketch whatever that function looks like over its domain, and from there you'll be able to literally observe what is the tallest or shortest y value that'll correspond to the minimum or maximum of your function. Once you see it, you just solve for that spot. Usually it's a turning point. Sometimes it could be an endpoint. If it's a turning point, use whatever methods you like for solving turning points. If it's an endpoint, you literally just sub in the x value of that endpoint. So let's try an example. We have a fence, rectangular garden, 20 meters total of fencing wire. What is maximum area that can be enclosed by the wire? So we got 20 meters total. Pro tip on this one, whenever you have anything rectangular, the maximum area is always going to be a square. So if you think about like taking this 20 meters and arranging it out to look like a square, you're effectively just going to have like 5 by 5. So very quickly you could say this is just going to be 25 meters squared. The procedure I'm showing you here is more so for when it's not so cut and dry, when there is no real shortcut involved. So there's a fun little shortcut for these. But okay, let's pretend it's more complicated than it is. If you wanted to find the area of a rectangle, you always find length by width. Problem is, you've now got two variables that you're dealing with. You've got a length and a width. Not great. So ideally, we only want to get it down to one variable. That's where this other piece of information comes into play. The fact that we have 20 meters total of fencing wire means that our total perimeter of that shape is going to be 20. And if you think about how the rectangle works, it's going to have two lengths and it's going to have two widths. So the addition of those two things should give you the total 20 meters. From there, you can actually pick which of these variables you want to rearrange for, unless the question forces you to pick one. I've chosen to rearrange for W and then get my equation in terms of L. You could rearrange for L and get your equation in terms of W. It's not actually going to change. From there, you just sketch that graph. So if you pretend these L's are X's, then that just means you're going to have a cut at x equals 0 and a cut at x equals 10 from this. And sure enough, that's what we see here. Now, we don't necessarily want the entire graph, because when you're dealing with these kinds of questions, you now need to really dig into the fact that the y and the x-axes are supposed to be like, quote, real-life quantities, where the y-axis in this case is area, and the x-axis is the length. So think about how that works in real world. You can't have negative area, you can't have negative length. So effectively what that means is you're just going to chop off everything there, and you're just left with the positive portion of your parabola. From there, you can literally just look at the tallest y value, and that is your maximum. If it was a minimum, then you'd be looking for these values, in which case you'd give minimum area of 0, and that corresponds to lengths of 0 or 10 in this case. So yep, in this case we're doing maximum, so we care about this spot here. You're not going to have that y value immediately. You're going to have to find it. So there's a bunch of ways you could find your turning point. Because this one has x-intercepts, and the application style questions pretty much always have easy x-intercepts, the best way I know for solving turning points under these circumstances is just find the midpoint of your two axes intercepts. Midpoint, of course, being x equals 5, which we knew from before, right? A length of 5, a width of 5 would maximize, would turn it into a square. But we're going to have length equals 5. You sub that into your area equation and you get your 25 meters squared. Don't forget the unit. So there's a long-winded way of doing a simpler kind of question, but when you check in the book, there are ones that are certainly more complicated than this. They'll talk about things like energy. They'll talk about other weird, wacky stuff that you can't necessarily intuitively know is going to be your maximum or minimum. There are some circumstances where there's not a turning point. So even if we took that simple example of the rectangle, if one length cannot exceed 4 meters, then suddenly when you go through all the steps from before to create your equation and you draw your graph, you realize that you actually have to cut it off here. You can't have this entire thing because of this statement here. Length cannot exceed 4 meters. So the only portion of the graph you're allowed to use is this one, the new maximum is now going to occur at L equals 4. And so you sub that in, maximum is now 24 meters squared. That's the gist of it, really. Anything else in there needs to be clarified, or shall we get on to some questions? And if so, which kinds of questions? Would you prefer the last document or the first document to work on first?
I don't mind.
Either's fine. Okay. Cool. Let's see if we can grab one that's more. I've done these relatively recently. Maybe we could even just go for the chapter review instead. These are going to have some weird stuff. Oh yeah, they sure are. Okay. Let's have a look at some extended responses. So, we've got an arch. It spans 50 meters. The shape of the curve is a parabola, so that part of the bridge is a parabola. This is our water level. B is the highest point, so you can think of that as like your turning point of the parabola. A is going to be the origin in this case, and we're told the maximum height above the water level is 4.5. So if this is the maximum height, the highest point, then this is going to have a 4.5 associated with it. Write down the formula for the curve, where y is the height and x is the horizontal distance from A. So a good point of order would be to just start drawing this yourself on your own axes. It does say that A is the origin. So if we go to the handwritten section, it's going to look something like this. So 50, we have some turning point that's going to belong up here. It says y is the height, so that's going to be y. It says x is the horizontal distance, so x is going to be that. Now we need to give this equation. There's some information in it that we haven't put down yet. What might we start to do to get closer to the equation of this? I'll grab a screenshot of the full question as well, so you don't have to keep pinging back and forth between the two screens. That'll be in the chat as well. What can we do about that 4.5 meter? What's that going to look like on our graph?
That'll just be the height of the turning point.
Yeah, precisely. It's going to be the y coordinate of the turning point. Nice. 4.5. It's in terms of meters. Everything in here is in terms of meters. Cool. So pretty close to getting the full coordinate of that spot. How are we going to get the x at that spot?
Sub in the point to the equation.
Sub in a point? Sure. So what equation are we starting with? Because this one wasn't, like, that's just elsewhere. Remember, we've got to be a bit strategic with what kinds of equations we start with based on what information we have.
Could you say that the x-intercepts are at the origin and x equals 50?
Yeah, absolutely good. So it's going to be origin, x equals 50. So based on that, what would you likely use for your equation?
The x-intercepts form.
Yep. So you'd have y equals a bracket, well, x take 0 is just x, and then x take 50. Nice. All right, what could we do from there?
Sub in the y value of 4.5.
Yep. So if you sub in 4.5, you're going to have an unknown a and an unknown x in there. It's a bit tough. When we have two unknowns, we usually need two equations to solve those two unknowns. Not necessarily a bad thing right now. How else could we potentially find this spot? Because if we knew an x at 4.5, then we could solve for the a pretty easily.
Oh yeah, just be 25.
Yep. 25, because turning points, now I know my drawing isn't perfect, but the midpoint of your axis intercepts will always be the x value of the turning point. So all these x values going to be replaced with 25. That's just, what, 25 squared there? No, negative, then 25 all squared equals 4.5. These extended responses are CAS, of course, and so let's just do that instead. 31. No, don't even need that really. It's just 4.5 divided by, so 25 times 25. It's negative, yeah, divided by negative 25 squared. And so you're going to get an a value of negative 9 over 1250. So final answer, y equals minus 9 on 1250 x take 50. That's certainly one way of doing that perfectly fine, yeah. Another potential method here would have been turning point form. So now that we could quickly find our turning point, we could have done like x take 25 all squared plus 4.5 and then just solved for a. And solving for a would be subbing in probably 0, 0 would be the easiest, but 50, 0 is also there. But it's the same idea, right? Information gives you the starting point, sub in one of the other points to get the last one. Cool. It does say part B to calculate some table of values to plot the graph. That's just a waste of time, really. You just plot the graph with what's there. You only need x-intercepts and turning point, well, and y-intercepts, but yeah. Okay, part C. At what horizontal distance from A is the height of the arch above water level equal to 3 meters? What's that all about?
Just sub in y equals 3.
Yeah, y equals 3, because above water level is a y distance, horizontal will be the x. So yeah, because it does say at what horizontal distance, so we're solving for the horizontal, which is x. So the 3 meters would be the y. So again, this is CAS. So just use CAS. Let's take 250. Let's take 50. 31. 3 equals function, comma x. That's going to give us 2 spots on the curve because it is parabolic. You would give those as values just for the fun of it. If you control enter, you'll see it's approximately 10.5 and 39.5. So about like there and there-ish. That's that. Part D, very similar question. What is the height of the arch at a horizontal distance of 12? Pretty quick to say what's going on there. Very similar information.
Oh yeah, just x equals 12.
X equals 12, yeah. Now you're given the horizontal and ask for the height. So x equals 12. On the CAS, simple as just saying h 12. You give that value. I mean, I guess in this case decimal also works because that's a closed decimal. Okay, now this one, I remember going through this before in a previous class. This one was tough. So part E, we have a platform that is 20 meters wide and it's being towed under the bridge. what is the greatest height of the deck above water level if the platform is towed with at least 30 centimeter horizontal clearance either side. Now, that's a lot of words. What does that actually mean? Well, first things first, we're told that the platform is 20 meters wide. And so we want that to be, like if you think about towing something under this bridge, effectively you're going to have something that you're towing equidistant either side of this arch. That'll give you the biggest vertical clearance possible. So that total distance is 20 meters. So we're thinking about doing that from either side of 25. You're going to have, what, 15, 35? Yeah. So the x values of these spots are 15 and 35, if you think about what you're towing. Now, the goal is to figure out the greatest height that this could possibly be. So how tall can I make this thing that I'm towing before this distance, so from here to here, like imagine that's the peak, before this distance is breaching 30 centimeters. So I'm only allowed a horizontal clearance of 30 centimeters. What is going on there?
I think this is the question that I'd skip in a sec.
Pretty accurate. Yeah, this is the one you sort of come back to at the later time. Or maybe you draw a diagram-ish like that and maybe get a mark for the diagram. Okay, so the height is the thing that's variable. And so we're effectively just trying to figure out how high could it possibly be to the point where it's 30 centimeters. So if we redraw this to now, like properly depict that in a bit more detail, we've got some parabola. We're saying this distance here is 30 centimeters. This is also 30 centimeters. And we have some box like that that is parallel with, well, level with that. And that occurs at x equals 15 and x equals 35. If you think about these as y values, this like horizontal bit being some y value, this being some x, how are we going to get, because the height is going to be the total y value of this thing, right? Because this is y equals 0. This is y equals the height of the thing we're after. We have initial measurements here of 15 and 35. There's this further 30 centimeter clearance. How could we possibly get the y value here if the only curve we have is the curve of this quadratic? I'll give a further hint. These y values is the same as this height, which is the thing we're looking for.
Somehow find the x values.
Yeah, somehow find those x values. So this is 0 meters in, this is 15 meters in. There's a 30 centimeter gap between these two. 20 meters later, you're here. Another 30 centimeters from there, you're here. And this is, what, 50 meters? Yeah. So a couple of ways you could go about that. You've actually got two possibilities. If we know this is 30 centimeters away from 15 meters, then getting this x value that touches here would just be 15 meters minus 30 centimeters. Right, because it's 30 centimeters to the left. That'll give you some x value that intersects the curve. That curve's y value at that spot is the height. Same thing over here. 35 meters, 30 centimeters away from that, plus your 30 centimeters to 35 meters, you're going to get this x value, which touches the curve here. This y value is the height there. So you could do 35 meters. Like usually addition's a bit nicer to do. So you're going to have what, 35.3, because 30 centimeters, yeah, 100 centimeters to a meter. Yeah. So 35.3, whatever the y value is at that spot, should be our target. 3.736 for a y value, which makes enough sense because our absolute maximum is 4.5, so already we're a bit below that, which is good. We don't want to have exceeded it. And yeah, that's the gist of it really. So you have your 35.3, or you'd have the opposite, which is 15 minus 0.3. So again, you're going to have that exact same y value, and that becomes your height. Is it at all clear why that's the height?
Are they still going to do these types of questions in the Year 12 exam?
Possibly. It's on the harder side for sure to get your head around. They might leave it, let's say, tech active. They usually chuck some weirder stuff. Yeah, it's possible to do this. It's a reasonably difficult, not super like separator style question. The kinds of questions they really put in to mess with you would be when you have like a slider involved on the CAS. They'll have like a bunch of unknowns in a function. You'd have to play around with what the function looks like on your graph and then just sort of go from there. Whereas these ones have pretty analytical solutions, where it's just like, yes, there's a very determined and streamlined way of getting there. As long as you're able to set up your picture of what's going on, then things are things are very cut and dry. There's only like one way to go about it, really. This is kind of similar to, we'll bring up a similar question. It's kind of similar to what happens when you have like shapes that are inscribed into other shapes. And you'll see what I mean by that in a moment. Okay. I put this in calculus, yes. This is a much older document, so it's not particularly great. It uses this idea of the fact that getting a y value can only be done by getting it from the curve. So if you look at we have for the screen share, this was a tech-free question, kind of similar. You're given this semicircle relation, and there is a triangle that has been inscribed into that. So you've got the vertices A and B, which are known. B is kind of unknown, actually. It's got an unknown x. But because P is vertically up from that, it's going to share whatever that x value is, and it's going to have some unknown y. And we're trying to figure out what's the maximum area of this triangle. Now, if you remember what we do to start off all these kinds of questions, you want to create your expression for whatever the thing is you're looking for. If it's area of triangle, then it's going to be a half times base times height. That's just stock standard for triangles. Now, from here, you want to get this purely in terms of a single variable. In this case, they've already put x in there, and so ideally we're going to get everything in terms of x. So, from here, the base of this triangle is the length from A to B. If you think about how you do lengths that are completely horizontal to each other, you're just doing first point minus second point. All right, so in this case, x minus minus 1, x plus 1 is that full length. You've got this length here, x, added to this length here of 1. We want our lengths to be perfectly positive. So that's going to give us an expression for our base. The height is given by the y value at this spot. Much harder. Not much harder. It's using the same idea that we did before, which was in our bridge equation, we didn't have this rectangle's dimensions, but we did have the dimensions of the parabola, the support structure around it. In this question, we don't have the triangle's dimensions, or at least not a lot of them, but we do have the equation of the semicircle. So if we figure out the y value of the semicircle at this spot, that is the height of our triangle at that spot. It's the same idea. Now the way that works is you figure out what the x value is here, if you can, or you just plug in whatever generic x they've given you. So in this case, instead of saying the value is y at this spot, we can say it is root 1 minus x squared at that spot, because that's what y is. And just like that, you have your full equation of area purely in terms of x. Is it making a bit more sense now how we can use the surrounding equations to figure out related heights?
Yep.
Cool. Okay. Might as well finish this one off from here. So if you want to find maximum area at this spot, plotting this yourself, tough. Yeah, very tough to plot that yourself. And so this is where you'd use, I don't know how many of you have done calculus yet, but you'd use something called a derivative. Derivative effectively finds turning points. So if you remember what we were doing in the previous question, to find maximum heights, we would do find a turning point. So that was like that was this one here, finding turning point. What we find is if you take the derivative of a function and make it equal to 0, then you get the y value at that spot. Yeah, you get the value at that spot. Was that a question, Jake, or was that just the reaction?
Just the reaction.
Sure. Okay, so derivative. This is where you would do something called the product law. Now, I'll breeze over this because this isn't quite the topic. Point being, if you have a product of two terms, then you find its derivative using this equation. Fancy, whatever. Yeah, ignore like, okay, that's a lot. You get this expression, you equate it to 0. Point being, you now have this method of getting the x values for which there is a maximum. We won't worry about the specifics there. That's for a later time. You're going to have two possibilities because it was a quadratic at the end. X is either -1 or x equals 1/2. If you look at the possible x values here, x equals -1 is over here. X equals 1/2, we could say, is about there. If I were to choose x equals something, which of those is likely to give me the maximum area, given that x is setting this? So if I put x here, I get a triangle like that. If I put x here, I get a triangle like that. Which x value, -1 or 1/2, is going to give me the maximum area?
Sorry, what was the question?
So we had two possibilities for x after we looked at some nonsense equation to get there. The possibilities were either x equals -1 or x equals 1/2 would maximize the area of the triangle. Okay, so if we look at our triangle, x equals -1 is over here, x equals 1/2 is here. If x is the like the height, sets the height of your equation. So if x is here, the height will be that. If x is here, the height will be that. X is here, the height will be that. It basically just intersects the curve there. Which one is likely to give the maximum area? If I put my height here, or if I put my height here?
If x is 1/2.
Yeah, x is 1/2. X is 1/2, you've got a massive height that's here. If you put it here, you actually have no area. So this method of derivatives, which looks a lot nastier than it actually is, I promise you it's a bit better. This method of derivatives not only finds maximums, but could also find minimums as well. Okay, we know x equals a half is our only valid solution, so to find the area, we plug that into our area equation. So area equation, just replace all these x's with a half, simplify it all the way down, maximum area achieved. Apparently this was a tech active question, and I just decided to be insane and show you how to do it tech free instead. Yeah, no wonder it was a mad thing. Anyway, I'll leave it at that. So, point being, you can use related shapes, related equations to figure out shapes, the dimensions of other shapes that are related to that. That's about it for this one. If anyone has any final questions, feel free to stay behind. Otherwise, enjoy the rest of your life. Take care.